In the second part of section 12.5, we're going to learn about curvature. So curvature is the measure of how sharply a curve bends. For example, in figure 1, you can simply tell that point P has a greater curvature compared to point Q because the curve bends more sharply at point P than point Q. Actually, you can calculate curvature by calculating the magnitude of the rate of change of the unit tangent vector t with respect to the arc length s. When you are actually trying to figure out curvature, there are three formulas that you need to get familiar with. The first one is definition of curvature. Let C be a smooth curve in planar space given by r sub s, where s is the arc length parameter. The curvature k at s is given by k equals magnitude of dt over ds, or magnitude of derivative of t sub s. One thing to be noticed here is that t sub s is equal to derivative of r sub s over the magnitude of derivative of r sub s. The second one is when given a curve function by r sub t, then the curvature k of c at t is given by k equals magnitude of derivative of t sub t over magnitude of derivative of r sub t, blah blah blah. The third one is curvature in rectangular coordinates. If c is the graph of a twice differentiable function given by y equals f sub x, then the curvature at point xy is given by that function. So these three formulas are just really straightforward. When you see problems like these, you can just plug it in. Those three formulas are going to get you through, so we're not going to do any example here. Finally, let's look at acceleration, speed, and curvature. We all know that acceleration function is the derivative of speed function, and speed function is the derivative of position function. So if r sub t is the position vector for a smooth curve, the acceleration vector is given by a sub t equals that, where k is the curvature of c and ds over dt is the speed. Here we need to introduce two more important concepts, tangential component and normal component. A sub t is tangential component, which equals to second derivative of ds over dt. A sub n is the normal component, which is equal to k times ds dt squared. Many times when you are solving application of acceleration, speed, and curvature, it's no different than the previous questions we talked about. And when you are asked for tangential component and normal component, they are just the coefficient of t and n in the acceleration vector function. And remember, whenever you have doubts doing homework, there's always the summary of velocity, acceleration, and curvature table at the end of section 12.5. Whenever you have any doubts or couldn't remember a formula, just refer to that table and you're going to know everything. Finally, let's look at one example. So if we have this curve function given by r sub t equals 2ti plus t squared j minus 1 over 3 t to the cube k, we want to find the arc length, tangential component, and normal component. So first, let's find the curvature. So it's not apparent whether this parameter represents arc length. So we should use the formula k equals over. And now we have to find derivative of r sub t. So r sub t derivative is just 2i plus 2tj minus t squared k. And now we can find the magnitude of it. The magnitude of derivative of r sub t is just 4 plus 4t squared plus t to the 4th power, and that's just going to give you t squared plus 2. And t capitalized T is just derivative of r sub t over its magnitude, and that is 2i plus 2tj minus t squared k divided by t squared plus 2. And that's derivative is negative 4ti plus 4 minus 2t squared j minus 4tk divided by t squared plus 2 squared. And its magnitude is just 2 over square root plus 2. And now we know that curvature is 2 over t squared plus 2 divided by magnitude of derivative of r sub t. And that is just t squared plus 2. Now, we know the curvature is just 2 over t squared plus 2 squared. So next, we want to find the tangential component and normal component. We know that ds dt equal to magnitude of r sub t derivative, which is t squared plus 2, and curvature is 2 over t squared plus 2 squared. Now we can find the tangential component, which is a sub t equals second derivative of ds over dt, and that's just t squared plus 2's derivative, which is 2t. And the normal component is just curvature times ds over dt squared, and that is 2 over t squared plus 2 squared times t squared plus 2 squared, and you get 2. So that's how you find the curvature, normal component, and tangential component. I hope these are all helpful, and good luck studying.